Okay, awesome. I think we can start. Welcome everyone to another of the CERN container webinars. Today we have Fernando and Fahui presenting to us how Atlas is using Kubernetes to run some of their compute sites. This should be really interesting. As usual, feel free to drop any questions in the chat box or in the Q&A. And then at the end, we will go through them. So thanks a lot for giving this webinar, and go ahead.
Right, thanks a lot, Ricardo, for inviting us. So as Ricardo already mentioned, the purpose of this presentation is to show a bit how the project that we have been running in the last almost 2 years to integrate Kubernetes clusters with the Atlas workload management in a very lightweight way. Before we get right into the topic, just some words of introduction. Both Fahui and I work for the University of Texas at Arlington, but we are actually based at CERN. In my case, by education, I'm a software engineer. And after university, I came to CERN. I've had different roles in Atlas distributed computing. And since 2015, I'm part of the PanDA team, which is the system that takes care of all the workload management for Atlas across the worldwide LHC computing grid. So I will pass it to Fahui, so he introduces himself and he will show the first part of the presentation.
Okay, thanks, Fernando. So I'm Fahui. I come from Taiwan, and I joined PanDA team at CERN as a software engineer 2 years ago. And yep, so next slide. Yep, so here is the outline for today's talk. So I'm going to talk about the PanDA server harvester pilot paradigm, which is the main model in Atlas distributed computing, and motivation for native Kubernetes batch integration and the implementation details. And then Fernando will continue with CVMFS details on Kubernetes clusters and resource overview, examples on commercial clouds, and then he will perform a quick demonstration about building an Atlas compute site with Kubernetes on commercial cloud. Okay, so next slide. So yeah, so PanDA, as known as our production and distributed analysis system, this is a data-driven workload management system designed to meet Atlas production and analysis requirement in an LHC scale. And all production and users tasks are submitted to PanDA. And Harvester is our service to interface any compute resources working with PanDA server. And Pilot is an execution environment to monitor and execute payload on compute node. So you can see the diagram. So all the analysis and production tasks of Atlas are submitted to PanDA server. And meanwhile, Harvester gets some information about PanDA jobs. Then Harvester know how many jobs to submit. Then Harvester will submit to the batch scheduler, and this batch scheduler is a part of the site which manage the compute resource under the site. And eventually the pilot will run on one compute node in this resource. And the pilot will communicate with PanDA server to get the real PanDA job to run and update job status and etc. So that's the model in brief. Okay, so next slide. And about Harvester, this is our universal resource interface. And it can talk to lots of different resources because it's plug-in feature. So one can see that a Harvester can run with HPCs in different configurations depending on the security restrictions or network restrictions of a normal HPC center. And Harvester can also run with grid. And in this case, it talks with usual some usual counter CEs ArcCEs, etc. And Harvester can also work with cloud resources. So Harvester can spin up and submit jobs to cloud managing virtual machines or containers in Kubernetes models. Okay, so next slide. And here we show you the scale of Atlas Grid. So the plot on the left shows you that there is a distribution of slots per resource type, including grid, cloud, and HPC. And as you can see, we have about 500,000 slots of running jobs in total, and a grid is the majority. And as the cloud part, it's actually most composed of a CERN 0.1 resource. And on real clouds, we have a few slots, but not too many. And the plot on the right shows you the distribution per site. So our these 500,000 cores are composed of many sites distributed all over the world, but all handled centrally with PanDA system. And you can also see different sizes of these sites. We have big sites like CERN 0.1 and CERN tier 0. And they have tens of thousands of cores. And we have smaller sites, for example, in tier 2, tier 3, which have only hundreds of cores. Okay, so next slide. And let's talk about some background for Harvester Kubernetes integration. So Atlas was using a heterogeneous, Atlas is using heterogeneous computing infrastructure for batch workloads. So, and the integration was historically done by various teams in various ways. And then PanDA team developed Harvester as a universal resource interface 3 years ago. And this was more or less the same time as the first Atlas Google proof of concept base. So we were looking for lightweight and generic cloud integration. And in the first proof of concept, we implemented direct GCE virtual machine lifecycle management. And it worked. However, there is a VM creation overhead as a downside, and also it was only specific to GCE platform. So therefore, Harvester team came up with another idea that's just to make the native Kubernetes integration. So it also worked, and it has less overhead. And Kubernetes is more generic. It is available in many major clouds and some high energy physics institute. And it can also be used to host services. It's very easy to deploy as a lightweight or opportunistic site. Okay, so next slide. Yeah, so there are many advantages and possibilities of Kubernetes integration. First, Kubernetes has native container environment, and we like this feature. And in theory, the Kubernetes has standard interface across all major cloud providers and WCG clusters. And this is a critical advantage for us. And Kubernetes has, and in this Kubernetes model, we have a massive infrastructure simplification in comparison with the grid batch sites model. Yeah. However, we are losing some grid features in experience in exchange of discovering some new behaviors and experience on Kubernetes. And since early 2020, mini Kubernetes grid with central harvester has been growing. So we currently we have a couple of hundred cores in each site, in Academia Sinica, in CERN, in University of Chicago, and in University of Victoria. And we also have some ongoing projects with commercial clouds, say Google and Amazon, and the Oracle project is being set up. Okay, so next slide. Yeah, so And here comes some details for this Harvester Kubernetes integration. So in our model, Harvester submits Kubernetes jobs as workloads on the Kubernetes cluster. And according to the official Kubernetes document, a job creates one or more pods and ensure that a specific number of them successfully terminate. And this is the feature we want. So in our model, we map one Kubernetes job to one batch job. So it works like this. Harvester submit jobs, and each job runs one pod, and pilot runs in the pod. And Harvester monitors jobs and pods, and after the job finish, Harvester deletes them. And one thing to notice is that we don't use the retry mechanism in Kubernetes jobs. So if container fails, then the pod will fail, and then the job will fail. So we have these set up in the configuration. So the backup limit equals to is equal to 0, and the restart policy never. And that is because we managed the job retry on PanDA side, so on a higher level. Okay, so next slide. Yeah. So here, this diagram shows you an overview of the Harvester Kubernetes. So for Kubernetes, all we had to develop on the Harvester side was to implement the resource-specific plugins, while the complex intelligence is generic and implemented in the Harvester core. So you can see these plugins on Harvester side, which communicate with Kubernetes cluster. And say the credential manager plugin, this one, it shares and updates proxy certificates through the Kubernetes secret. And the submitter plugin creates the Kubernetes jobs. The monitor plugin pulses the cluster to check the status of current jobs and pods. And the sweeper plugin cleans up the jobs after they finish. And in the Kubernetes cluster, you can see that each job contains the pod, and pilot runs in the pod and communicates with PanDA and some storage. And you can see there are different size, different shape of pods, because pods are submitted with different shapes of resource requirement. For example, it can be 1 core, 2 gigs memory, or 8 core, 16 gigs memory. And this is according to requirement of Atlas jobs. Okay, so next slide. And here is an example of a Kubernetes job we have in YAML. So, and for sure, this it has kind job, and the backup limit and restart policy, as we mentioned, we don't enable them. And you can see the container. It has the executable downloaded from GitHub, and this is the code to run the pilot. To start the pilot to run. And you can see other commands and some environment variables. And on the bottom, you can see the image. This is the image name. This image is maintained by Atlas, and it is a CentOS 7 image with various package pre-installed. And on the right, you can see the resource requirement. So in the CPU and memory requirements and limits. And these are filled dynamically according to the Atlas jobs. And on the bottom, you can see the pod in the job needs to mount some volumes, including the volumes for CVMFS and the secret for VOMS proxy certificate. Okay, so next slide. And another detail, so about pod affinity. So in Atlas, among Atlas job, we have 2 resource type. So the S core or single core, that means the job only use 1 core, or is either M core, so multi-core, that means the job requires more cores. It's usually 8 cores. That means the job requires the whole node. And sometimes it's 4 core or something else. And in each pod, we have the label on about the resource type on the pod. So the problem we had was by default, Kubernetes spread out pods across the node. So it may cause some inefficient situation. For example, each node only runs 1 or 2 single core pods. The node still has plenty of empty slots, but the multi-core pod cannot fill in the node. And there may not be enough single core pods to fill the node either. So we will have some empty slots unused. So to tackle this, we set pod affinity policies to fill the slots more efficiently. This includes the single core and multi-core have anti-affinity against each other, and the single core has affinity to the single core itself. Thus, single core pods tend to gather on the same nodes, and that means multi-core pods have more chance to get a whole node. And here is an example of YAML file. So you can see the labels. In the labels, this pod has resource type multi-core. And on the right, you can see this pod has the affinity policy. It's pod anti-affinity against single core. Okay, so next slide. And this is an example after with the pod affinity policies. So this shows you one of our Kubernetes sites with 320 slots. And the plot shows number of slots in running jobs. And you can see multi-core jobs in brown, red, and single core jobs in blue. In this plot, sometimes there were more single cores and sometimes less, depending on the need of Atlas jobs. And with the affinity policy, you can see that except for a small dip when single core decreased, otherwise the utility of it was pretty stable and the slots were filled almost all the time. Okay, and yeah, from now on, Fernando will continue. So Fernando.
Okay, thanks, Fahui. So there are also 2 components that we need on each Kubernetes cluster, and this is CVMFS and Squid. I tried to show in this diagram a bit what does a Atlas job actually do inside the pilot. So the first step is to download input files into the pod. And then it runs a transformation, which is Atlas software, which processes this input file and generates an output file. All of this Atlas software is distributed through CVMFS, and this is a big dependency in Atlas on CVMFS, and how the software is distributed on all the resources in grid, HPC, and cloud. And then the other component is this Squid that is being used to retrieve some frontier conditions data in some jobs. And we also need to set up a Squid for our clusters. Now, setting up the frontier Squid is fairly uneventful. You just have to set up you can do it either through a dedicated virtual machine, or in the latest exercises, we also implemented the Squid inside the Kubernetes cluster so that it's self-contained. But the deployment of CVMFS is a bit more tricky, and it needs to be installed through a daemon set plus Kubernetes volumes, and I will show some details in the next slides. I want to give a bit more information about the CVMFS installation methods, since I think that some of you in the audience are also people that have worked on the CVMFS CSI driver, and I wanted to give my general opinion and feedback. So the easiest way that you can install CVMFS on your Kubernetes cluster is directly on the node through the package manager, through YAM or through RPM. This is the most stable solution, but it's not always possible if you don't have direct access to the node, or if you have a dynamic Kubernetes cluster where the nodes come and go. For these cases, there are 2 solutions. Both are more or less similar. They consist of a daemon set that installs a pod running the CVMFS package, and then some auxiliary volumes that help to mount the CVMFS into the different pods that are running the jobs. For those that don't know, a daemon set is one of the Kubernetes controllers, and its main function is to ensure that there is one copy of a pod on every node in your cluster. So all of the nodes will be running a CVMFS copy. And if a new node is getting added to the cluster, then the daemon set ensures that this new node also runs, in this case, CVMFS. And if a node is removed, then that copy of CVMFS is garbage collected. The first option to run CVMFS as a daemon set is the CSI driver. It's the implementation of this container storage interface standard with some methods to bind and to mount the CVMFS into all the different pods. It's implemented by CERN IT, and it was also the first solution that we knew and that we were using in our clusters. However, at least for me, it's a bit complicated because I'm not a Golang developer. And then it's difficult for me to do any troubleshooting and correct the issues. In the last months, we heard about another solution which was implemented by the Pacific Research Platform. The idea is very similar, but instead of implementing the container storage interface, they are just sharing a local volume. So the implementation is a lot simpler. And we made a fork of this solution with the Atlas requirements, and this is the solution that I'm using currently at most of my classes like CERN, Google, Amazon. The other thing that is very important about running these CVMFS drivers is setting correct CPU and memory requirements. So, for example, by default in the CERN OpenStack cluster, at least some months ago, when these drivers are installed directly by the cluster provider, they have no CPU or memory requirements. This makes that these CVMFS drivers run under the best effort quality of service, which is the lowest priority. Then on the other hand, as Fahui showed during his part of the presentation, our jobs, we submit them with CPU and memory requirements, and they go in particular to this burstable quality of service. So they rank higher than CVMFS driver. And when the node is full, which is very frequently the case in our Atlas clusters, it means that the CVMFS drivers will suffer. In particular, if the node is full of memory, then the CVMFS driver is very likely to be killed the first. And but there you see an exact error message, and you know what has happened. On the other hand, because of not specifying the CPU requirements, this causes that if the CPU is full, then Kubernetes is not giving any CPU cycle to the CVMFS driver, and it becomes extremely slow. And the first thing you think, since it's a storage cache with network access, you think there is either a network problem downloading the files into the cache, or the storage is somehow malfunctioning. But it's actually the CPU that is blocking this, the driver to work. And requesting a small amount of CPU for us, I think we put it 0.1 CPU and memory just 100 or 200 megabytes, goes a long way and solves the situation. In this slide, you have an overview of what are the Kubernetes queues that we are currently operating. So the bottom four are a cluster that we have at CERN. This is running under our Atlas R&D quota. This one was recently halved in September. That's why it drops. There is no problem there. Then we have a cluster in the University of Chicago, Chicago operates a very big Kubernetes cluster with a lot of things going on there. They use it for multiple experiments. They install different software components, and they let us run a couple hundred cores with Atlas jobs. And then University of Victoria and Academia Sinica are sites that actually like this Kubernetes model a lot, and they have been there since the beginning. And in fact, for example, for University of Victoria, their plan is to next year move more resources into the Kubernetes mode and reduce their resources that they are providing via like grid standards and computing elements. And on the very top, you see from time to time we have some contributions. This one is Google, and here you have a couple of resources from Amazon, and these are some commercial cloud projects that are going on that I will show in the next slides. Just to mention, here on the right you see the overall failed wall clock consumption. This is a combination for all the queues. It's 8%. This is very similar to the general grid infrastructure. And it varies a bit depending on which of the queues you look at. There are some queues that are very stable and have a lower failure rate. But then also, for example, in Google, we run preemptible resources, and those are much cheaper, but increase the failure rate a bit. So coming to the commercial cloud projects, the first one is some project that we are running between US Atlas and Google. The scale is not so big, it's around 200 cores, but we have run it over several weeks and tried a lot of different configuration and payloads. So we have gained significant experience with Google. There were two stages. In the first one, what we were doing is running simulation jobs. The simulation jobs are typically the entry point for any new cluster to try it out. They are CPU intensive, but they almost don't have any IO requirements. They just copy in a couple megabytes of input and write out a couple megabytes of output and run for a couple hours with full CPU. And in this case, that's why it's possible to run the storage where the input is copied from at CERN and not inside Google. But then on the second stage, we also integrated the storage at Google. So we have a bucket in GCS, and all the input and output is read and written to here. And in this case, it's possible to run IO intensive jobs, and we try to use some end user analysis from a colleague of us. And well, you'll see in the next slide some details on the node tuning that we had to do. So the first stage is the simulation cluster. As I said, these jobs have low IO. The storage is at CERN. We were running preemptible nodes at Google. The characteristics of preemptible nodes are that it's kind of the leftovers from the high-paying customers, and they can run for a maximum of 24 hours, but they could get killed earlier. And for this reason, since they maximally can run 24 hours, we were limiting the job duration to be brokered to this queue to under 5 hours. Since the longer the job, the worse your failure rate will get. But it is an attractive deal because the price is around 70%, 80% cheaper, but the failure rate just goes up from whatever, 8% to 14%. So it is a good deal. The other option that we were using is auto-scaling. Since we were limiting the jobs to under 5 hours, there were not always jobs brokered to the queue. And that you see here in the diagram as these empty, the faults in the resource usage. And auto-scaling in this case, since it sees that there are not so many workers queued, it scales down the cluster and you effectively pay less. And well, then the shape of the the diagram during time is also a bit depending on what was the budget that we had and how we were trying to schedule this simulation versus the analysis exercise. The overall cost of such a cluster was around $2,000 per month for in average 150 cores. And this includes all the output being copied to CERN, and because in commercial clouds you usually pay for the egress outside of the cloud. And now on the second stage, where we were running the user analysis and had already the storage integrated in Google. So this is actually the first time that I'm aware of where Atlas attempts to run like a full site inside the cloud, including the compute nodes and the storage. This is thanks to integration effort from Proothio FDS and also the grid middleware to integrate these three storages. And here our volunteer user wanted to analyze a dataset that was 1 terabyte in size. This dataset, we copied it into a bucket here in GCS. And then all the different jobs that our volunteer user was running, they had to download from GCS into the worker node between 2.5 and 12.5 gigabytes of input. So it depends on, sometimes he was running with 1 file per job and sometimes with 5 files per job. We had a little side constraint, and this was coming from the data management part. Since we were getting assigned URL to download the files from GCS, and the expiration for the signed URL was 10 minutes. So it means that we had to, the last file had to start to be downloaded before this 10-minute expiration. And we were not seeing a bottleneck here, but we were actually seeing a bottleneck here in the throughput that the node had to its disk, the disk that was attached to the virtual machine. And this is because Google throttles the throughput to the different resources in order to balance the usage across tenants. So that is so that, for example, Atlas doesn't come and completely abuses the link, and then other customers complain because they don't have throughput to the storage. And the ways that the solutions that you have to improve your throughput to the VM disk is either you upgrade to more performant storages. So moving from just spinning disk to SSD increases your link throughput. And then if you want to increase it even more, then you have to get local SSDs, which are connected directly through NVMe to the node. And the option that we went for was going with local SSDs, since those are actually cheaper than the network SSDs. And the price was more or less 50% more expensive than running the lower end virtual machines that we were running for simulation. And the other thing in this exercise that we have seen is that using preemptible nodes for user analysis is not very popular. You have to understand that in user analysis, it's a particular user that submits just a couple tens of or hundreds of jobs at one time, and is then following very dedicatedly what's the progress of his task. And if he sees some failures that he doesn't understand, then he gets confused. Whereas for example, for simulation, those are campaigns with tens of thousands of jobs that are checked only once in a while. We also have other commercial cloud projects going on more recently. In particular, we have one at Amazon that is a grant that is owned by the Fresno State University. And there I'm collaborating directly. And then there is a project in Oracle where University of Oslo, I think they have a contract, and a person from Oslo University is doing the setup for the Kubernetes cluster there. And my experience using these different clouds has been that the basic compute integration is straightforward, and you don't have to do any code changes in Harvester. Where you spend most of the effort is understanding the differences between how you set up the cluster in one cloud or in the other. Some have some network requirements. The way you set up the auto-scaling is different. Service accounts and stuff like that. Difference between preemptible resources and spot instances. Things like this. And in the bottom, you see the diagram of the latest progress at Amazon. And here we are running a cluster which is made out of spot instances. I have a bid of $0.1 per hour on a 2XL virtual machine. And you see that the failure rate is 3%. So it's really good, even with the usage of spot instances. Okay, so now we will come to the demonstration part. I've never actually done a demo, so I hope I don't blow this up. The purpose of the demo, it's not going to be something impressive, but it's to show you how simple it really is to now set up a PanDA queue in a commercial cloud. And I will try to set up just a very small cluster in Google and connect it to Harvester and see if a job starts to run. Okay, so then the first thing that we have to do is go here to Google Cloud Platform. This is just a project that I created for this demonstration. I have my own credit card behind, so that's why the cluster will also be small. I will go to the Kubernetes engine and I will create a cluster. Okay, so I will call the cluster demo. It's going to be zonal. I'm going to put it in Europe since it's going to be reading from CERN. So I typically take Europe West 1B. Otherwise, the versions I'm going to use the default ones. Now, if we configure the node pool that is behind the cluster, again, the default numbers, I'm going to just make it with one node. And here's where you can select, for example, if you want to do auto-scaling. If you would choose it, you can put the limits of, I want it to go between 1 and 200, and then it will grow or shrink depending on what's in the queue. And then when you go to the node configuration, any of the operating system images is okay for us. I will create a E2 virtual machine, and I will select it with 8 virtual CPUs and 32 gigabytes of memory. The memory is a bit too much for us. You can also take custom ones, but it's not necessary for this demo. 100 gigabytes of persistent disk. Here's where you configure if you want persistent, like spinning disk, SSD, if you want local SSDs. And that's basically all that you need to configure. I will create a cluster. Now this will take a minute or two. So while it creates, I will show you that, so on the IAM part, what I do is I create a service account. This I already created it beforehand. It's this one, the Harvester demo. It just has this Kubernetes engine developer role, which is from the default roles the closest to what I need. But you could also here, Google shows you what are the roles that you are actually using. And you see that out of the 200 something roles that permissions that this role has, we are only using 26. So if I would be very strict, I could just make a custom role for this and remove all the unnecessary stuff. The things that we need is what Fahouy showed. It's submitting jobs, deleting jobs, dealing with persistent volumes for the CVMFS, secrets to copy the VOMS proxy, and so on. Okay, so let's see if in the meantime the cluster created. No, it's still booting. Well, so in the meantime, here I have two sessions that are both to my Kubernetes cluster. What I will have to do is configure this GKE in my harvester configuration file. All that needs to be configured. I mean, we have a template for Kubernetes, and all that needs to be then overwritten is what's the template for the job that you want to use, and where is the kube config that you want to use. And then I will have to set the queue status to online. And the other thing that I need to do on my on Harvest is to set up the Google Cloud CLI to download the kubeconfig file. So that's why I have there the service account logged in. So for listing the clusters, so you see the cluster still in provisioning. This could have been faster for the demo. We need to still wait a little bit.
Do you want to take one or two questions, Fernando, while we wait, maybe?
Okay.
Yeah, so Samuel, I'll give you voice and you can ask. Go for it. Samuel has one or two questions.
Hi. Very nice presentation, by the way. I have some questions, but I think they could not be in the context of Harvester. I thought that it allows the users to submit jobs to the Kubernetes cluster. But I understand now that you need to deploy different clusters for each group or project that wants to run the jobs. Is that right?
Well, in Atlas, it's I mean, it's as Fahouy was trying to explain here. So all of the users are submitting the jobs to PanDA, and it's then PanDA who will decide to which of the sites it's going to be sending the job. And this decision is done depending on where is the data that the user wants to analyze, how full is the cluster already, and parameters like this. So you can force to use a particular site, which is what we were using for the user analysis in Google, where the user was saying, I want to run my jobs in the Google cluster. And then this was, PanDA was routing the jobs there. And for the user, he doesn't know if the resource that he's going to use is actually a Kubernetes cluster or it's a whatever, a grid site or an HPC. Does this answer the question?
Yes, thank you. And about authorization for the users, how it works. It uses your own authentication and authorization system, or?
So Atlas is based on X509 certificates. So how this works is that on the Harvester node, we have a long-living certificate that lasts for a year. And from this certificate, we are generating a proxy certificate that is valid for, I think, 3 days. And this is what the credential manager is doing. It's copying the 3-day proxy into the Kubernetes cluster. And then the pod has the proxy certificate available. And then here the proxy certificate is being used to communicate, for example, to get the input from the storage element and then write the output back.
Thank you very much.
Okay, so let's go back. Let's see if the cluster is ready. Perfect, it's done. Okay, so then what I still had to show you, this is getting in the way. So I have in the grid information system for Atlas, I created a queue. It's called GKE. The details that you care about, it's for example the status of the queue is test. So that means that it will only get test jobs. It's not going to be getting real jobs from any user. And then further in the configuration, you see that the queue is attached to storages that are at CERN. They are not at Google. And then further below, you can see like stuff. You configure how many cores the node has. It's 8, and what's the memory. I think I have somewhere here. It's 24 gigabytes per node. Okay, so and then on the PanDA monitor, let's refresh this and see that we have some test jobs queued since it's in test mode. It's still refreshing, okay. So we have 5 activated jobs. Activated jobs means they are waiting for a grid resource or Kubernetes resource to pick them up. Okay, so then let me check my cheat sheet. What do I have to do? Yes, I need to download the kubeconfig file. I will put it. This is if you export the kubeconfig. This is where the kubeconfig will be downloaded. This is done through the G-Cloud. That's the Google command line interface. I'm downloading the credentials for my cluster demo in Europe West 1B. Hop, it got created. So let's see if. So yeah, this is now perfect. So I can then activate. No, before I activate it, I need to install CVMFS. So to install CVMFS, I will download the CVMFS driver repository. I go to the branch GKE, which has some customizations for GKE. So what I first need to do is I need to create the namespace, which is CVMFS, where all the pods will be running under. Okay, it worked. Then I create a service account on the cluster. Done. Now what I'm going to do, this persistent volume root, what it does is just on the node, a local, it will declare a directory on the node as a volume. Okay, created. Now I will install a daemon set, which will spread one CVMFS pod on each node. Done. And now this creates in CVMFS, we have 5 volumes that we need for Atlas. So it's going to create all of them. And finally, just to check that CVMFS was created correctly, I will just submit a pod that basically sleeps there for a while. So let's see. So now I can do kubectl get pods, and the pod is creating. This can take a little moment. It's the first time it downloads the image, takes a bit longer. Okay, it's still waiting for the for CVMFS. This can take a minute. Maybe if there is still another question, we can do it in the meantime.
I was gonna suggest the same. So Tibor, just give me a second. Tibor, do you want to go ahead?
Hi, yeah, thanks. So I was wondering for your second example, what was the development challenges needed to make Rusio run in GKE, GCS, and basically how much effort was it? Can you comment a bit more on that?
Well, so I have worked on the workload management part. I have not worked on the data management part. I'm not part of the Rusio team. I think this isn't. It has taken effort and from a lot of different communities. Like some years ago, the third-party transfers that were possible, they were all using this SRM and grid FTP protocols. And in the last years, there has been effort from all this middleware community to implement compatibility with HTTP protocols and the implementation of this Davix library. And I think that building on that, the Rusio team has had to also do some changes on their side. But I cannot say exactly what are the changes that they had to do. But I think it's important to say this is a community effort from a lot of different parties to get that part done, that part working, and that now it's possible, in at least in small proof of concept, it has been possible to use a Google bucket as a Rusio storage element.
Thanks.
Okay.
There it is.
Running.
So then I can connect. I connect to it. I just see if we should have 5 CVMFS volumes. There they are. Okay, so now I can just put my queue in, my GKE queue in online. I restart Harvester so that it reads the configuration. And then if we go to the log files, we should see, for example, Harvester, this was now, so Harvester already submitted the proxy to the as a secret, so you can see this in the cluster. There it is, the proxy secret. And we should start seeing Harvester submitting workers. So this, we need to still wait for another cycle because it needs two cycles to submit. And then we should start seeing the pods coming in here. I'll do a tail. And when we see this updating, then we should be getting pods, and we should see the job changing in the web page. What I can show in the meantime, unless there is some question that someone.
There was a question about the monitoring of the jobs, of the Kubernetes jobs. How do you do that?
Well, so we monitor the PanDA jobs, and there are different options. So for example, here, this is the standard Atlas monitoring. And here you see how many jobs are running. And for example, I know that at CERN I should have 320, so here we are on 306, so that's working fine. And then also you see the failure rate, how it's evolving. And you can see, you see here, it's mostly green. There are peaks that are in red, and that, I mean, you need to see, you can see further down. You can see the, yes, the failures by the site. So this, for example, was the EKS, this was Amazon. So I suspect that there was some, with the spot instances, some turnaround of machines. And then also each cluster, you can monitor it here through get pods, you see. In the meantime, we got some jobs submitted. So you can see what's the status here. If you have a lot of failures, you can see top nodes to see if your nodes are used efficiently. There are a lot of ways. And then on the cloud providers, I can also show you here in Amazon. Let me make this a bit smaller. You see the cloud provider information. And you see here, this is a running cluster CPU utilization. If you look for a particular node, you can see that it's the usage is 100%, except for some periods where I suspect it's the job has finished. It is copying the output to the storage, and the next job will get the input in. But otherwise, it's 100% CPU efficiency. And yeah, and you see also here in the network out, there are those, that's when the output file is being written out and so on.
Okay, so there's a question from Olga. Just let me go ahead, Olga.
Hi. So in regards to monitoring, this is more of a question on how do you keep your eye on the costings. So since you're running on different providers, you need to basically get that information into your system, right?
Yes, so so far we had those, I mean, we had grants which, for example, were $10,000 and they had a deadline. So we were calculating more or less what's the size of the cluster that we need, and we were sizing accordingly. But then you really, I mean, you need to start looking in the web page of the cloud provider to see what's the breakdown of the different costs.
And so Harvester is not really, is it collecting any of the metrics or logs from the actual Kubernetes resource jobs, the actual job?
So Harvester does not know about the cost in dollars. That's not integrated. Harvester just, it sees the size of the cluster and the jobs that are assigned in PanDA, and will submit the batch jobs accordingly. But it doesn't know about dollars.
Okay, thank you.
And I mean, I think that's mostly it. Here I would have hoped that we see them changing status from activated to running. But I mean, so that's basically it. So you have seen how, yeah, running. The first one is running. So that's basically it. And just to show how within some minutes, I was able, instead, if I put instead of one node, I put 100, then I would have a big cluster running very quickly.
I think for everyone that has worked on the grid in the past, this is pretty impressive.
Yeah, and I mean, yeah, because back in the days, we would have to do work for weeks and custom code, putting complicated middleware in the cloud. And so all of this is, we avoided.
Yeah.
Okay.
So I don't see any other question. Are
yes,
you done,
and
or?
It's also...
Sorry, you have the conclusions. Go ahead.
I mean, we are done also with the time, so I don't want to extend this longer, but just it was to show how easy it is now to set up a cluster in the cloud. It has not always worked perfectly, But I think we are starting to get it right. You see the failure rates are quite acceptable. What I suffer the most is on the dependency on CVMFS, and we will see how that evolves with time. And also the fact that, like, if we could choose, maybe we would have taken an architecture that is more based on self-contained container images, but we need to be compatible with the general grid. And so we are marked a bit by that. And that's it from my side.
So you have more questions here. I'll give voice again to Samuel. Go ahead.
Just a question about the guide to try to do this exercise from this demo and try to use the Google, for instance, the Google service and try to do the same deployment. Do you have any documentation for it now or only this demo?
So you can see on GitHub HSF Harvester, under the wiki, we have different documentation on how to set up your own harvester. And then we also have at the bottom some setups for the different clouds or at CERN. This has evolved a lot in the last 3-4 months. So not everything is up to date, but it can give you a first impression. But the one thing that is maybe a limit. I mean, I don't know what you exactly work on, but the limitation is that this is Harvester is working together with PanDA, so it has to be the jobs have to go through the PanDA system at the moment. It's not something standalone that you can run.
That's fine for me. This is very interesting, and I will try it for sure.
And also for the Harvester part, Harvester installation, we have here on the PanDA WMS. There is a Helm chart to install. Here to install Harvester through a Helm chart, and if you don't want to do pip install and so on.
Very good, thank you. Excellent work.
Cool. There's another question from Thomas.
Hello, I had a question from earlier in the slides where you showed the pod affinity rules. Because you also mentioned that you have some 4 core jobs. I'm wondering how these fit into the pod affinity system. Can you have 4 core jobs running on the same node with 4 single core jobs, or?
So, I mean, this all depends on, the multi-core can be, it doesn't have to be 8, it could be 4, it could be 16. And also the node doesn't have to be 8 cores, it could also be 16. So this anti-affinity, it avoids a bit that you have a couple of single core jobs mixed together with a multi-core job.
Okay, so you can mix multi-core jobs of different sizes, but you just don't want to get single core jobs.
Yes, I think
into the mix.
I think that the most important part is that the single core jobs go together, because if they spread out, they can lead to a very inefficient usage of your cluster. Because if you have, for example, 8 core nodes and 8 core jobs and 1 core node, 1 core jobs, as soon as you get a 1 core job, then the other 7 cores can only be occupied by single core. That's why the biggest importance of this affinity stuff.
Okay, thank you.
Okay, awesome. I don't see any other question. I do have one very quickly. Sorry for extending this 1 more minute. But you mentioned the costs included the egress costs. Do you know what's the percentage of egress versus the computer?
It's important. I don't know the exact number, but maybe 30%. And,
yeah, okay.
and running simulation.
Right. Yeah.
We did other exercises which was more of a, it was not the workload, it was a data management exercise where Google was used as an intermediate storage. And there the egress was like multiple times the cost of actually storing the data.
Yeah.
So you have to be very careful with egress.
Yeah, I think there's some activity going there as well to get some better rates. The other one was very quick also. You mentioned that you were using local SSDs. We had issues with this when you have a large cluster, because actually there's not that many local SSDs available in some of these regions in GCP. Did you consider using memory storage instead of local storage?
It was suggested by one of our Google contacts, but if you want, I think that you cannot, like per machine, the maximum amount of per virtual CPU, the maximum amount of memory is, I don't know how many gigabytes. And if you need to store all the input files there, I think you run above that quota. Okay. I think that's why we didn't use this CVMFS.
In the past, you can actually use, there's a volume type that will just use memory. And we were using, but this was for analysis jobs where the files were 4 GB each. And yeah, you could have a few, you could have quite a few. And this solved the issue, because we tried local SSDs and then we run into availability issues where we couldn't have big clusters because they don't have enough in most regions.
Mm-hmm. Yeah.
Yeah. Cool. I don't see any. There's Thomas again. Go ahead, Thomas.
Oh, sorry, I didn't unraise my hand.
Okay, cool. Okay, so I think that's it, unless someone has anything else to add. So look, thanks really a lot, Fernando. This was an awesome webinar. Really, really cool demo. You should do them all the time.
Thanks a lot for the invitation.
And it worked. So thanks again to Fahui as well.
Thank you.
And yeah, thank you everyone for attending.
Okay, thank you. Bye.